In this Precalculus Algebra video, we'll look at inverse functions and how they relate to the function for which they are the inverse. Here's an interesting problem that you can find in your textbook, possibly. What's the probability that two people in the same room share a birthday? It might be higher than you think. In this section, we'll explore the graph of the function that represents this possibility. The purpose of this video is to look at this objective here to determine if a function is one-to-one, and if so, to find the inverse and describe its domain and range. Now, if you are completing Precalculus Algebra and this is one of your learning objectives, then by the end of this video, by the end of this section, you should be able to determine if a function is one-to-one. You, the student, should be able to find the inverse if the function is one-to-one, and you should be able to describe the domain and range of the function. Let's look at an example. If we have this function f of x is 3x, or 3 over x minus 4, and then given g of x is 3 over x plus 4, we should be able to find f of g of x, or find g of f of x. And here's what we know about inverses. By definition, if this result ends up being x, and this result ends up being x, if both compositions, f of g of x and g of f of x, end up being x, then what we can say about the two functions is that they have a special relationship to one another, and that relationship is that they are functions. Let's try this. If we have f of g of x, we're going to take the f function, 3 over x minus 4, but we're going to replace the x with g of x. That's how we do the composition of functions. If you need a review of that, I'd encourage you to watch the video that goes in more detail into composition of functions. But to find the composition of f of g of x, we find the g of x function and we put that in for x of the f function. So g of x is 3 over x plus 4. So that is what I will put in for x. The inverse, the composition of f of g of x is 3 over x plus 4 minus 4. Well, that's correct. That is the inverse, but it's not simplified. We can see right away that we could regroup these using the associative property and group the 4 minus 4. 4 minus 4 is 0. So we'd have 3 divided by 3 over x. It's not simplified if we have a complex fraction. A complex fraction is a fraction within a fraction. But if I rewrote this as 3 over 1 divided by 3 over x, that might give you a clue as to how we can simplify this. Here's how we would simplify it. Instead of saying 3 over 3 divided by x, we're going to say 3 over 3 and under, moving the whole frame, x. 3 over 3, and that 3 is under the x. So if you did this by dividing, remember 3 over 1 times x over 3. But you don't want to have to write this out every time. If you get in the habit of saying 3 over 3 and under x, this x is the one that comes up to the numerator. But 3 over 3, and then the x comes up to the top. The 3 over 3 is a 1. 3 divided by 3 is 1, so we have 1 times x, or just x. Let's find the composition g of f of x. For g of f of x, we're going to start with our g function is on the outside. So we've got 3 over x plus 4. And in place of x, we're going to put f of x, right? Well, what is f of x? F of x is 3 over x minus 4. So we have 3 over x minus 4. A complicated, complex fraction. You're going to have to do a little bit of algebra here. I'm going to rewrite this 4 as a 4 over 1. And there are a couple ways we could simplify this. One thing I can do is multiply everything by x minus 4 over x minus 4. But first, you want to understand this first step. But then after that, how to simplify it, we're going to get rid of that complex fraction. So in other words, get it so that we don't have a fraction within a fraction. One way to do that is to get the least common denominator, x minus 4, and to combine these. Another way, and the method I'm going to recommend here, is I'm going to multiply with the least common denominator being x minus 4, because the denominators we have an x minus 4 and a 1. If I multiply the numerator and the denominator both by x minus 4, so everything in the top and everything in the bottom by x minus 4, that's one way to get rid of that x minus 4. So we'd have 3 x minus 4 over 3 x minus 4 over x minus 4. Let me go back and color code some of those for you. In the case you're questioning, where did each of those come from? I've just copied them over, but let me show you where. Here's the 3 over, and then we had a red 3. This 3 is the one in the bottom. So you see what we've done is we've just put an x minus 4 in the top and in the bottom, right? So I've just multiplied that by 1. I can do the same thing. Actually, I'm not going to do that to the second one. I probably could have better written it like this. Let's wait to worry about that 4 after. So I'm just eliminating that double fraction. Do you see how it worked? Now I've gotten this x minus 4 over x minus 4. That x minus 4 over x minus 4 is just 1. And look at this. Those 3's happen to reduce also. So all I have is x minus 4 over 1, which is x minus 4. And then I'm going to go back and add my plus 4, this plus 4. So the 4 and the minus 4 cancel each other out, and we're left with an x. That got a little confusing. Go back and practice it a few times. There's not a one-size-fits-all or a here's the one way you can always do this. You just have to become better and better at algebra by practicing it and find the way that fits the best for you. Let's look at the definition of an inverse. Because did you notice in that last example that we got an x when we did f of g of x, and we got an x again when we did g of f of x? When you think about it, here's what's happening. We're starting with an x and putting that into the g function. So the x goes in, what comes out? G of x comes out. And we are going to put that g of x into the f function, and what comes out? F of g of x. But here's what we're looking for. If it's an inverse, then if the g and f are inverses of each other, that's a better way to say it, then what's going to come out is an x. You start with an x and end with an x, then we would call those inverses. I could reverse the order here also. Can you picture going backwards? If I started with the x and put it into the f of x, and what would come out? What would come out is f of x, right? So x is the input, the output is f of x. I'm going to plug that f of x into the g of x. If I get an x out of that, then we say that these two have a special relationship. They are inverses. You're familiar with inverses. Here's an example. If f of x says take x and add, pick your favorite number. Today my favorite number is 7. So take your x and add 7. And let's say that g of x is, now think about it, how do you undo adding 7? What's the inverse of adding 7? It's going to be subtracting 7, isn't it? So if the first machine adds 7, so in goes an x, what would come out? 7 more. And then the second machine takes that x plus 7 and subtracts 7. What's going to end up? We've got our x back. Would it make a little more sense if we tried it with a number? Pick your favorite number. Let's say a 10. A 10 goes in. 10 plus 7 is 17. 17 goes into the second function. Now 17 minus 7, what comes out? A 10. Look at that. We started and ended with the same number. Try it going the other direction, starting with the pink one. If we go in with a 3 and we add, I see that I already did the f of x first for this one. So let's do the g of x first. If we take our 3 and subtracted 7 from it, 3 minus 7 would be negative 4. Put our negative 4 into the pink function. Negative 4 plus 7 would give us our 3 back. Those are inverse relationships. Can you think of other operations that have an inverse operation? Did you say multiply and divide? You're right. Yeah, multiplying and dividing undo each other. What about squaring? Can you think of how to undo a square? Yeah, that's right. You square root it. Squaring and square rooting, they undo each other, right? If we have a 9 and you square root it, you get a 3. If you take the 3 and square it, you get your 9 back. Are you familiar with Dr. Seuss and the Starbelly Sneetches? Come by my office and I'll tell you what, you can take your picture with a Starbelly Sneetch. If you can find my office, you can take a picture with a Starbelly Sneetch. Doesn't that sound exciting? My Starbelly Sneetch is wearing some green beads. So you're welcome to stop by my office when I'm there and see the Starbelly Sneetch. But if you're not familiar with the story, we've got this commotion going on in a community where the Starbellies think that they're better than the Sneetch without a star. So this guy comes into town and he makes a machine that if you go in, it'll put a star in your belly. So now these ones who didn't have a star, they have a star. Well, then the ones who had a star are like, I don't want a star anymore. It's no longer the popular thing to do. So he reconfigures his machine so it removes the star. And you could see the star going on the belly is the function, and then the inverse function is the star coming off of the belly. Really interesting way to see that if you're familiar with that idea. Well, let's move on to how to find an inverse. You should know the answer to this one without trying, because we just did one like this, right? If f of x is x plus 3, I can guess that the inverse is going to be x subtract 3, right? This is my guess. But let's see, and let's make sure we have a process. Here are the steps. The first step is you replace f of x with y. So I'm going to go to the function, and in place of f of x, I'm going to put a y. So I'll replace f of x, that notation, with y. Step 2, interchange x and y. So the x becomes a y and the y becomes a x. And then solve for y. I'm going to do some algebra here to solve for y. How would you solve this thing for y? If we wanted to solve for y, we'd subtract 3 from both sides. We'd have y equals x minus 3. And then the last step is going to be to put it back in function notation. So the notation would look like this: f inverse of x. So it looks like an exponent of -1, but the way we read that is f inverse of x equals just what we expected. We're brilliant. X minus 3. We got it. Let's try another one. The practice of just using this process. Replace the f of x with y. So I'm going to get rid of the f of x and just change it to this notation. Because, you know, y and f of x, they mean the same thing. It's just two different notations. So I'm just replacing those. And then next I'm going to, I will interchange x and y. So the y becomes an x and the x becomes a y. And now I want to solve for y. When you look at this, do you remember how to solve for y when the y is cubed? How can we undo a cube? We can undo cubing with a cube root. So I'm going to do the cube root of y plus 2 cubed, so that this cube and cube root undo each other, and I'm left with y plus 2. And if I cube root the right, I've got to cube root the left. Don't get too carried away with this, because to solve for y, all I'll need to do is subtract the 2. When I subtract 2 from both sides, I have y, because these 2's cancel each other out, equals a cube root of x minus 2. That's all there is to it. Other than writing it in the final answer form, f inverse of x equals the cube root of x minus 2. Now be careful not to blend those together. We don't want it to look like that. -2 is in the radical. Inverse of f of x, when f of x is x plus 4 over x minus 2. What do we do first? We replace the f of x notation with y. What do we do next? Interchange x and y. So the y becomes an x, the x becomes a y. And now it's just solve for x. Or, I'm sorry, what am I saying? Solve for, did you catch that? What do we want to solve for? Solve for y. Here it is, solve for y. So when we go to solve for y, this one's a little bit more complicated, but it's doable. What I'm going to use is a special tool called cross multiplying. We could see this as an a over b equals c over d, right? We have because if I write this x as an x over 1, fraction equal to another fraction. Do you remember the cross multiplying? The a times d would then equal b times c. I'm going to use that tool. X times y minus 2, cross multiply, equals 1 times y plus 4. If you didn't quite get that, pause the video, rewind, watch it again. It's like watching a movie and missing a scene. And wait, how did that happen? So just pause it, rewind it, try it again to make sure you get this. When you look at this expression, do you see what could be simplified if I'm trying to solve for y? If I'm trying to solve for y, I'm going to have to distribute this x. So I'm going to multiply x times y, and I'm going to multiply x times -2. So we'd have xy minus 2x equals y plus 4. And now, as I look at this, I see if I'm going to isolate the y's, I need to get all the y's together and all the x's together. So how about if I subtract y from both sides and add 2x to both sides. Do you see that would get this 2x over to the other side? And it would get this y over to the other side. So let's try that. And what would we have? Let me erase some of those circles to make it a little clearer as you're looking back at it. So I would have xy minus y, negative 2x plus 2x cancels each other out, y minus y cancels each other out, equals 2x plus 4. Remember what I'm trying to do, trying to solve for y. Don't give up here. The problem is long, it is drawn out. You have to be persistent. You have to have confidence that you know what you're doing, and you do. You do know how to do this problem. It's basic algebra. It's just that it's a whole bunch of basic algebra steps, one after the other. So you can do it, but you just have to be persistent here. I'm going to factor out a y here. Since I'm trying to solve for y, if I factor out a y, I get y times x minus 1. Do you see that? Y into y would give me x. Y into y gives me 1. So I could factor out a y. Or in other words, I'm factoring xy minus y by factoring out the GCF y, this green y. So y times the quantity of x minus y equals 2x plus 4. The last thing I would need to do to solve this is going to be to divide both sides, because remember what we're trying to do. We're trying to solve for y. So to isolate y, I'll then divide both sides by x minus 1. So we have an x minus 1 over x minus 1 is 1. So y equals 2x plus 4 over x minus 1. And writing that in the correct notation, the final function notation, f inverse of x is 2x plus 4 over x minus 1. And that's how you find an inverse. We could check that these were inverses. If you did f of g of x and then g of f of x, you could verify that they are, in fact, inverses. For number 3 here, we can use a horizontal line test to determine if a function has an inverse. If the function passes the horizontal line test, I know you're used to the vertical line test. The vertical line test tests if a relation is a function, right? Is it a function, yes or no? Both of these are functions. But the horizontal line test tests if the function is what we call 1 to 1. If it's 1 to 1, then it has an inverse. Notice that on the left, this absolute value does not have an inverse. It's not 1 to 1. It does not pass the horizontal line test. But this function does pass the horizontal line test. So we say, yes, it has a function. Number 4, we could use some information about a function to find its inverse, but from the graph. So what I have here is these pink points, 0, -4, 2, 0, 3, 2, 4, 4. I've graphed those. Watch what happens for the inverse. For the inverse, the x and y swap, right? Do you remember that in the process of finding an inverse? The x and y swaps. So the y becomes an x, and the x becomes the y. Here's the y from f. The y of f becomes the x of f inverse. Here's the x for the function, 2. That 2 becomes the y. So I just reverse 3, 2 becomes 2, 3. Out 4, 4. In reverse, it's still 4, 4. Just like dad or taco cat, in reverse is still dad or taco cake. If you haven't heard that one, try it. What happens when we graph these? I've got the f function graphed in its color. The F inverse is graphed in blue. If this was a continuous function and if we connected the points, we'd see that these were both a line. But look at this line, x equals y. I've graphed this x equals y on here to show something. If you were to pick up your device and tilt it so that this dotted line was vertical, going up and down, you could see that we've got a mirror image on both sides, right? This is how we tell that a function is an inverse by its graph. Two graphs, the graphs of two functions are inverses of one another if they're symmetric on the line y equals x, or f of x equals x. That's this line, y equals x. And because we have symmetry across that line, we know that they're inverses. One more problem with this. This is the last one. Find the inverse of the function and graph it. So let's find the inverse really quick. I'm going to switch the y with x and then solve for y. To solve for y, I'll take the square root of both sides. But remember the square root property, I've got to do the plus or minus the square root of the part that wasn't squared. So this square and the square root undo each other. We have y minus 1. Sorry, I didn't mean to write that here. We have y minus 1 is equivalent to or equals plus or minus the square root of x. Solving this for y, I can add 1 to both sides. So y equals 1 plus or minus the square root of x. Or in inverse notation, f inverse of x is 1 plus or minus the square root of x. If I were only interested in the x's that are less than 1, if I'm only interested in the x's that are less than 1, we can look at the graph and see which of those we're going to use. So 1 plus the square root of x or 1 minus the square root of x. We'll come back to that. Let's look at the graph really quickly. If we were to graph that f of x equals x minus 1 squared, I'm going to recognize that that's a parabola that shifts 1 to the right. So I can do these 3 points. And I could even say that for 1 over 1 more, we'd go up 1, 2, 3, 4. 1, 2, 3, 4. So here's our parabola. But if I'm only interested in the x's that are less than 0, then I'm only going to be interested in, let me use another color for it, in this blue part, right? Because we only want the x's where x is less than or equal to 1. So I could erase this part of my graph to fit that domain. Now, if I graph the inverse, I could do this just by changing these points. So why don't I name each of these points? And I can see that the inverse is going to have the inverted points, right? So instead of 1, 0, we'd have 0, 1. Instead of 0, 1, we'll have 1, 1, 0. Oops. Here's the 0, 1, 1, 0. And then instead of negative 1, 4, we'll have 4, negative 1. So we'd get this graph. So that blue graph and the pink graph are the two functions graphed side by side. Good practice is to finish a graph up to the end of the graph that we're given, the coordinate plane that we're given. And do you see how helpful it was to use two different colors? I recommend that with the graphs, use two different colors to show each of the function and its inverse. Well, I hope you found this helpful. Let me know if you have further questions about the topic.